Welcome to the deep dive. You were curious about the fundamental building blocks of our planet, the materials all around us.
Yeah, the ground beneath our feet.
Exactly. So we're taking a journey down there. We'll explore different soils, the rocks, and the whole world of metals. Okay, let's dig in.
It really is remarkable, isn't it, how all these, well, seemingly different things connect. Let's start with the soil, the very foundation.
Good place to start.
We basically got three main types. There's clay that tends to be alkaline, then loam, which is, more neutral, often has silt in it,
Okay.
and sandy soil. That usually leans more acidic.
And those pH differences, they matter quite a bit, right?
Hugely.
Yeah.
It affects everything, what plants grow, how water drains. It's fundamental.
Absolutely. And then right below that soil layer,
Yeah.
rocks. We're talking igneous ones first, like granite.
Yep, igneous, granite, basalt, sees basalt from cool lava flows, and even pumice, that really light, holy one.
Formed from molten rock, magma, cooling down.
Exactly. Whether it cools quickly above ground, like in a volcano making basalt,
Mhm.
or really slowly deep down making granite, that changes how it looks and feels.
Makes sense. Okay, then the metamorphic types. Slate, marble.
Beautiful stuff. Marble and anthracite coal, quartzite too.
They sound like they've been through something.
They have. Metamorphic means changed. Existing rocks get transformed by intense pressure deep down, or heat from nearby magma,
Or plates colliding.
or massive forces when tectonic plates smash together. Think of limestone, right?
Yeah.
Squeeze it, heat it for ages, and bam, you get marble.
Wow. Okay, and the last group. Sedimentary.
Sedimentary rocks,
Yeah.
like chalk, limestone, sandstone, those layered cliffs?
Yeah.
Mudstone, flint, coal, again, but a different type, and claystone. These really feel like, well, history books.
Because they're made of layers.
Exactly. Tiny bits of older rocks, minerals, sometimes bits of plants or shells, sediment. It all settles down, usually in water.
Lakes, oceans.
Lakes, oceans, yeah. Then it gets buried, compressed over millions of years. Each layer is like a little snapshot of the past. Finding a fossil in there, that's amazing.
A direct link. So fiery starts, intense pressure cooking, slow layering. Quite the story for rocks. Okay, let's shift gears. Metals, nonmetals, alloys.
Right, metals. We generally think of them as conducting electricity, being solid.
Pretty standard stuff.
And nonmetals usually don't conduct electricity, but there's always a curveball, isn't there?
Let me guess. Carbon.
You got it. Carbon, specifically as graphite, does conduct electricity. Kind of weird for a nonmetal.
That is unexpected. Okay, and alloys, those are the mixtures.
Mixtures of metals, yeah. Like bronze that's ancient, copper and tin,
Capronickel.
copper and nickel, brass is copper and zinc. Stainless steel, everyone knows that one iron and chromium keeps the rust away.
And rose gold. That's gold and copper.
Yep, gives it that pinkish color. Alloys are all about tweaking properties, making something stronger or shinier or more resistant, like cooking.
A recipe with metals. Cool. Now, how do they behave? Their reactivity. Metals plus oxygen?
They form metal oxides. Simple one. Metal plus oxygen gives you metal oxide. Think iron rusting.
Okay. And metals with water.
That gives you a metal hydroxide plus hydrogen gas.
Hydrogen gas.
Ah, the test.
The squeaky pop test. Collect the gas, light it, pop. Always fun.
Memorable. Okay, and metals plus acid.
Similar outcome in a way. You get a metal salt and hydrogen gas again. Metal plus acid gives metal salt plus hydrogen.
But the really interesting bit was displacement, wasn't it?
Oh yeah, displacement reactions. Basically, a more reactive metal can sort of kick out a less reactive metal from its compound in a solution.
Like a chemical bully.
Huh. Sort of. It's all about which metal wants to react more strongly. It's a competition. That's why copper can push silver out of silver nitrate solution. Right, because copper's more reactive. This reactivity thing, it explains how we find them too, doesn't it?
Absolutely. The really unreactive ones, gold, silver, platinum, you can find them just as they are. Pure elements. Nature's treasures.
Lucky finds. But most metals.
Most are found combined with other elements in ores, like aluminum locked up in bauxite.
So you need to get them out, extract them.
And how you do that depends entirely on how reactive the metal is. For something like copper, maybe just heat and carbon will do it.
Silver.
Sometimes just heat is enough if it's not too tightly bound. Iron needs a blast furnace, serious heat,
And the really reactive ones, like aluminum.
like Klingon tight.
Yeah.
You need electrolysis,
Mhm.
using electricity to literally split the compound apart.
Electricity is the key, like forcing them apart.
Exactly. And electricity is also used for electroplating.
Right, putting a thin layer of one metal onto another. You see it in jewelry.
Jewelry, stopping rust, making things look shiny. But important point, it's just a coating.
It doesn't make the thing stronger underneath.
Nope. Just protects the surface or makes it look good. Common misconception that it adds strength.
Good to clarify. Wow. Okay, so from the soil way down deep through rock formation to how metals react and how we get them, we've covered some serious ground.
We really have. It's amazing how these basic materials, shaped by geology and chemistry, just build everything.
It really puts things in perspective.
And a final thought, maybe? Think about that reactivity series we talked about. It's not just for industry. You see it everywhere.
Like how some things rust faster than others.
Exactly. Or even how elements move around in the environment. It makes you wonder, what other everyday materials have these hidden complexities if you just, well, look a little closer.